Welcome everyone to this session, GOB303, Increase Your Architecture Resiliency with Chaos Engineering using AWS Fault Injector Simulator. My name is Paul Sears, and I'm a Senior Solutions Architect with Amazon Web Services, and I am based in Manila, Philippines. I have been with AWS for 6 years, and I'm a subject matter expert in AWS Well-Architected Framework. I will begin the session talking about the modernization journey through innovation of your workloads. Your architectures can increase resiliency through adoption of modern architecture patterns. As a stop along the way, we are going to briefly talk about well-architected, and specifically the reliability pillar. And then I will give you a brief introduction into chaos engineering, which is a foundation for today. I will then introduce to you a number of tools that help with chaos engineering. But the main focus of this session is the AWS Fault Injection Simulator. I will demonstrate how FIS can help you improve the reliability of your workloads through controlled experiments. Many organizations, likely even your very own, want to increase the pace of innovation, but face a delicate balance between adopting and managing technology and building new features. But the value gained from innovation allows you to get more from your data and to enhance your customers' experience. To start this modernization journey, you need to consider how you will build and operate your workloads. What architectures will you adopt? Modernizing your legacy or monolithic workloads involves a combination of modular architecture patterns, serverless operational models, and agile developer processes. To help with your journey, AWS offers you solutions. For example, your organization might be considering adopting containers, or maybe you already have container-based workloads. The next step in the journey would be to move those workloads to manage AWS container services, such as ECS, EKS, and Fargate, with the benefit of simpler operations and reduced management overhead. Or maybe you are designing a new application stack, or building in a new set of features. Or maybe you are finally breaking down that legacy monolithic application stack. We recommend that you consider serverless technologies, such as AWS Lambda, which is a serverless event-driven compute service that lets you run code for virtually any kind of application or backend service without provisioning or managing servers. A key stop along the modernization journey is the adoption of best practices in designing and operating workloads in the cloud. The AWS Well-Architected Framework helps you understand the pros and cons of decisions you make while building systems in AWS. By using the framework, you will learn architectural best practices for designing, operating reliable, secure, efficient, and cost-effective systems in the cloud. These best practices have been distilled from years of experiences operating extremely large-scale workloads in the cloud. AWS Well-Architected has 6 pillars, but the focus of this session is resilient workloads under the reliability pillar. The key principles of well-architected reliability are 1. Automatically recover from failure, 2. Test recovery procedures, 3. Scale horizontally to increase aggregate workload availability, 4. Stop guessing capacity, and 5. Manage change and automation. Now that we understand the well-architected approach and best practices for resiliency, how do you determine risks in your application architectures? You may already understand what to do for simple architectures. What about modern, highly complex applications? Chaos engineering is an approach that relies on chaos theory, which focuses on random and unpredictable behavior. We can use the principles of chaos engineering to form a hypothesis on how a system will behave based on a normal, steady state when that system encounters unexpected failures. Knowing the steady state of a system is critical to creating the hypothesis that you will attempt to disprove through controlled experiments. Steady state is the perpetual system behavior you are attempting to achieve. Once you understand the steady state, you form a hypothesis that the steady state will continue in the event of an unexpected failure or disruption. You test your hypothesis through controlled, real-world experiments that attempt to break the steady state to uncover weaknesses in the architecture of the system. Through the discovery of failure points, you can implement appropriate changes to address the system weakness. There have been many tools developed for chaos engineering experiments. One of the very first tools was Chaos Monkey, part of the Simian Army, that was developed by Netflix in 2011 and released to the open source community. Other tools have since been released, including the Chaos Toolkit and Chaos Mesh, which is designed for experimenting on Kubernetes clusters. These tools are very useful and can help with experimenting through chaos engineering, but they do require a significant amount of effort to deploy, manage, and update. In late 2020, AWS announced a new service, AWS Fault Injector Simulator, a fully managed service designed around chaos engineering experiments. As a managed service, you can quickly create experiments by selecting targets, actions, and stop conditions through the AWS FIS console without having to deploy and maintain any infrastructure. AWS FIS allows for safe experiments and rollbacks through controls and guardrails, as one of the guiding principles of chaos engineering is to minimize the blast radius. It is important to test the steady state hypothesis through introducing targeted disruptions rather than disrupting multiple components of the system at the same time. Experiments are defined in an experiment template. An experiment template contains one or more actions to run on specified targets during an experiment. It also contains the stop conditions that prevent the experiment from going out of bounds. After you create an experiment template, you can use it to run an experiment. An action is the fault injection activity that you run on a target using AWS FIS. FIS provides pre-configured actions for specific types of targets across AWS services. You add actions to an experiment template, which you then use to run experiments. A target is one or more AWS resources on which an action is performed by AWS FIS during an experiment. You define targets when you create an experiment template. You can use the same target for multiple actions in your experiment template. Let's have a look at the demo to show what I mean. So now we will take a brief look into the AWS FIS in action. In this demo, I will show the console and explain experiments, actions, and targets. First, we log into AWS console and access the FIS service. It might show up in your recently visited, as it does for me, if you have recently explored or used FIS. Otherwise, you can enter FIS in the search box. Select FIS and you will be taken to the FIS console. On the left sidebar, you should see experiment templates and experiments. Templates are what define the experiments that you will run. Experiments show the status of any experiments that you have previously run. The console home also provides an overview of how FIS works, pricing, and links to documentation that can help you understand the service, including the user guide. To create an experiment, you first create an experiment template that defines the actions, the targets of the actions, and any stop actions. I will create an experiment template to demonstrate the various actions that you can take on a target for your experiment. When creating an experiment template, you enter a description for the experiment. I will call mine Demo 1. You can also provide a name that will be used as a value for the name tag. You will also need to select a role to use for your experiment, as FIS will need permissions to execute the action on the target. I will use the role that I previously created for this demo. You will need to create your own roles for your experiments. Next, you will define an action. You can have multiple actions by adding more actions in the experiment. Provide a name for the action, an optional description, and select the action type you want with a drop-down list. As you can see, there are actions related to CloudWatch, EC2, ECS, EKS, RDS, and SSM. I will select the action AWS EC2 Stop Instances. For actions, you can also start instances after a specified duration to recover from your experiment if desired. When you create your action, a target is created, which you can edit to select the resources that will be targeted by this action. You do need to save the action that you are editing before adding more actions or selecting targets. Also, experiment templates can have multiple actions that you can run in sequence or in parallel. You then select your target resources on which to run the selected actions. You can select different resources types. I will choose AWS EC2 instance since I want to stop an instance as part of this experiment. You can select the instance using resource IDs or tags, filters, and parameters. Once you select the resources, You add them to the target definition, and then you are ready to create the experiment template. You can define stop conditions by selecting CloudWatch alarms that have been defined that will halt the experiment when the alarms are triggered. You can log the results of your experiment by either sending the log data to an S3 bucket or to CloudWatch logs. Finally, you can add custom tags to your experiment template. When I create my experiment template, I am required to enter a confirmation as my experiment doesn't have any stop conditions defined. This confirmation is simply to make sure you understand that your experiment could go out of bounds. You can review the details of the experiments you have created, as well as exporting the JSON of the experiment template. Personally, I find the JSON as an easy way to see all actions and targets instead of selecting different tabs in the console. Next, we'll look at experiments. This will show you experiments that have been previously run, including any status of the run. You can view the details of the experiments to understand what were the actions and targets selected, as well as the results generated. This allows you to explore the history of the experiments and understand any errors that may have caused an experiment to fail. Hi everyone, hope you enjoyed the demo. Now that we understand the basics of FIS, we will conduct some experiments on a common workload pattern, which is a single server instance hosting an external website, running a web server, connecting to a database. Often the website and database are on the same database server instance. The steady state of the workload is a website that can be viewed through a web browser and that visitors can access the information they are seeking. Failures in this steady state negatively affect the user experience of the visitors. Our hypothesis is that the website will continue to function normally as we introduce real-world disruptive activities, such as a failure of the web server or of the database. You might already have an understanding of these failure points, as this is a very simple workload architecture. But as the complexity of workloads increase, failure points might not be so obvious. Will our hypothesis be proven true? Let's find out. I have a simple architecture consisting of an EC2 server and a database that will simulate a typical web-based workload, which displays a simple web page and image. It is unfortunately a common deployment pattern to deploy a single web server, which often hosts a database as well. The website might have been developed as a simple server and grew into production. Additionally, it's common to not implement any kind of observability, relying on customers to report any issues. I have already created an experiment template, and I'll review the template so you can see the action and target that I have selected, which in this case is EC2 stop instances. As part of the action, the experiment will restart the stopped instance after waiting 1 minute. The target for this experiment is a single web server. You can also view the experiment template JSON, which I personally find easier than viewing the individual actions and targets of the experiment template in the console. Remember, following chaos engineering principles, we will set a hypothesis that the website will remain operational, and then we will use these experiments to disprove the hypothesis. To start the experiment, I select it and then click on Start Experiment. I see a reminder about logging. As well, I have the opportunity to tag this specific experiment run. I then click on Start Experiment to initiate it. You are presented a final confirmation to acknowledge that you're running an experiment that might perform destructive actions on your AWS resources. Enter the confirmation and then start the experiment. The experiment will initiate and begin executing specified actions on the targets. As you might notice, the website quickly becomes unavailable as the experiment is running, performing the actions in the sequence from the template, which in this case is to stop the web server, then restart it after a 1-minute wait. You can observe the status of the experiment in the FIS console. In this case, it is still running since it hasn't completed all the steps. The website is no longer accessible, and looking at the EC2 console, we can see that the web server instance is no longer running and has entered into a stop state since the experiment uses the action EC2 stop instances. Since we specified a wait duration of 1 minute, the experiment continues to run, waiting for the interval to complete. Then the experiment will restart a stopped EC2 instance. You can see now in the EC2 console that the instance has been started. If we check the FIS console, you will see that the experiment has completed successfully, as it has completed all the actions that were defined, including restarts. It takes a few minutes for the web server to restart. Finally, the web server has finished restarting, and after a few moments, the website has returned to steady-state operations. We can verify this by looking at the instance information in the EC2 console, as well as verifying by watching the website finally refresh in our second browser window. Again, you can also see that the experiment has completed in the FIS console. The results of the experiment run are now included in the experiment's history, and selecting the experiment allows you to see the details of the experiment used. If the experiment encountered errors, you can examine the results and adjust the experiment as necessary. Through this AWS FIS experiment, we were able to disprove our hypothesis as the system was not resilient. Failure of the web server resulted in errors on the website, and failure of the database also resulted in errors on the website. When the instance was restarted, the website returned to steady state. Thus, the experiment executed through AWS FIS revealed issues with resiliency. How can we improve the system architecture for increased resiliency? We will get to the answer shortly. But before we build a better architecture, we also need to mention observability. One critical component of resiliency is having visibility into the performance of the system. How do we know if the system is performing in the expected steady state unless we have observational data to validate the system? We collect data through monitoring, tracing, and logging. With large, complex systems, it can be difficult to know what to monitor. How do we know what we don't know? Experience through chaos engineering can help reveal blind spots in the observability of a system, in addition to weaknesses in architecture design, which can be improved to increase reliability. How do you implement observability? You monitor the system through metrics. You trace application flows, and you collect log information. Through observability, you alert on system behavior that deviates from steady-state performance. You then assess the impact of the behavior on the system to follow with taking appropriate action. The data collected through observability provides a direction in removing failure points, resulting in improving reliability of the system. For a deeper dive into observability, please watch the session GOB302, Implementing Observability in Distributed Applications. Now back to the question on how we can improve the system to increase resiliency. With the data collected from our experiments, along with data collected from observability, monitoring, tracing, and logging, we can greatly improve on our architecture and align with best practices. The new architecture design eliminates failure points revealed previously through the experiments we conducted with FIS. First is the use of AWS auto-scaling, which allows the system to grow, shrink, and replace instances of the website across multiple availability zones in an AWS region. We also add in a resilient shared file system, Amazon EFS, for storing code and assets that is common for all the web servers to perform at steady state, and also simplifies maintaining the upgrading code. This also reduces the startup time of an instance, as the code and assets don't need to be copied to the instance upon boot. Further in the backend, we set up a secondary database instance in a separate availability zone to allow for it to take over in the event the primary instance experiences a failure. Or we could configure the database as a multi-AZ cluster, where the secondary could be used for read queries for improved performance, if our application code allows for it. To further increase reliability, we leverage other AWS services which are highly resilient, such as Amazon Route 53 for DNS, allowing a failover to other application stacks if this architecture becomes unhealthy. Amazon CloudFront provides caching on static content, which reduces load on the web servers, as well as latency for visitors accessing the website. We also use S3 for storing of some static content, which as media files rather than serving this content from the web servers. Let me take a brief step back and focus in on the shared file system we are using in our best practice architecture. A shared file system can be accessed by all web and application servers that allows easy scaling up or down based on load, resulting in true elasticity. When you have a set of web servers or application servers, it is likely they have a set of common but changing assets. Without a shared file system, those assets need to be replicated to every web or application server or somehow incorporated into the base image used to launch those servers. For highly responsive scaling, the servers need to start as fast as possible. By using a shared file system, shared assets can be added or removed as needed without requiring application or creating a new Amazon machine image. If you currently have websites served from on-premises infrastructure, you might already have network-attached storage that is providing a shared file system. By moving those file services to AWS, you gain agility, reduce costs, and scale more quickly. AWS has shared file services that can support any architecture design, including on-premises and hybrid infrastructures. For example, Amazon FSx for NetApp ONTAP provides the same NetApp experience with the agility, lower costs, and faster scale from AWS. In our architecture, since our web servers are Linux-based, I am using the NFS-compliant Amazon EFS for shared file system. Maybe you are familiar with WordPress websites where you frequently need to update plugins and themes. By placing these onto a shared file system, the updates only need to be applied once for all the servers to gain benefit, even as they are scaled up and scaled down based on demand. Shared file services such as Amazon FSx and Amazon EFS also facilitate your application modernization and should be part of your architecture portfolio. For the final FIS demo, I have deployed the best practice architecture with a load balancer, an auto-scaling group, and RDS database with multi-AZ. I have also added a few CloudWatch alarms, such as watching for 500 errors or EC2 instance status check failures, and any RDS errors. I will use these alarms as a stop conditions for my experiment. I created 2 new experiment templates, tagged as Demo3 Stop Web Servers and Demo3 Database. I could have created a single experiment template and included both the EC2 action and the RDS action, but I wanted to do each separately to facilitate the demo. In the Demo3 Stop Web Servers experiment template, I will issue the action EC2 stop instances with the condition to restart the stop instances after 1 minute. For the target, I selected all 3 web servers currently running, but I changed the selection mode to count with a limit of 2, so that 2 of the 3 instances will be stopped randomly. As the web servers are deployed across multiple AZs, it is unlikely that all would be disrupted by a failure of an AZ or localized issue. This could also simulate real-world activities such as patching of the web server fleet, where instances would reboot during the patch process. You can also select targets based on resource filters and tags, which allows more flexibility in dynamic target selection. This allows you to create very complex experiment templates without having to manually edit the targets for each experiment execution. In the Demo3 database experiment, I will issue the action RDS reboot DB instances since my database instance is not configured as a cluster. However, the database is deployed as multi-AZ, meaning that it can fail over to a separate instance in a different availability zone. I also specify a stop condition of a CloudWatch alarm for HTTP 500 errors. Since we have the best practice architecture, our hypothesis that our website will remain operational through these disruptions should still remain valid. We will use these two experiments in FIS to try to disprove our hypothesis. First, I run the Demo 3 Stop Web Service experiment and monitor the steady state for any signs of disruption. While I have CloudWatch alarms defined, we will also watch the browser that is set to constantly refresh the web page. If the experiment disrupts the steady state, we will see the impact immediately on the website. Once I acknowledge the risks of performing the experiment, I can start it. As we see, our website remains fully accessible during the experiment. FIS has stopped instances in the auto-scaling group, but one remained healthy since I limited the count to 2 instances out of the 3. The database is unaffected by this experiment as it was not a target of any actions the FIS experiment completes once it executes the start instances on the targets after the defined waiting interval. As you can see in the target group, the load balancer is replacing the rebooted instances as they are unhealthy. Eventually, the target group is back to 3 healthy instances. With this experiment, we were not able to disrupt the steady state. Therefore, our original hypothesis holds true. In the second experiment, I will force a reboot of the database server, and I will force a failover to the backup instance. Our hypothesis is that the steady state will remain and the website remains available. Let's see what happens. Will this be the case as it was for the web servers? While the experiment is starting, I check for any CloudWatch alarms and I look for the status of the database server. As you can see, FIS has initiated the failover of the database instance, which takes a few minutes to complete. The experiment completes as the action has been completed, but the database is still failing over. Also, you might have noticed something. The web page isn't refreshing any longer. This is an interesting and unexpected behavior. Checking the status of the database, we see that it is now rebooting and there are now alarms in CloudWatch for the state of RDS. The web page is not refreshing, it looks stuck. Look, the website is now down. What is happening? This is supposed to be a resilient best practice architecture. However, disruptions of database servers often have greater impact. In this case, as the database server is failing over to the secondary server, the web servers are no longer able to connect to the database. Eventually, the database recovers on the backup server, and the website recovers automatically as the web servers can once again connect to the database. Additionally, it appears the failure of the database causes the health checks for the web servers to fail as they time out because they are blocked connecting to the database. So the load balancer replaces them since it believes they are unhealthy until the database recovers. Was this expected? Maybe we've learned some important things about our architecture from running this experiment. It takes a few minutes for everything to recover and the website to refresh properly. Once again, our visitor can access the information they need. FIS keeps a history of all the experiments. Both the web server experiment template and the database experiment were executed successfully by FIS. Additionally, if I had requested logs to be collected, I could access them in an S3 bucket or through CloudWatch logs. Using the experiment results, system weaknesses can be identified and we can make appropriate improvements to our architecture. Through FIS experiments, we have learned that the web server layer of the best practice architecture is resilient and is able to recover failed instances without disruption. But we found that the database layer still has resiliency risks. This allows us to focus efforts to address risks in the database layer, possibly implementing a caching layer using Elasticache, or configuring the database as a cluster with read replicas. But this is a topic for another session. As our session is coming to a close, let's recap what we covered. Chaos engineering is a methodology for discovering weaknesses in systems by developing a hypothesis around steady-state behavior and then performing experiments to disprove that hypothesis. We also explored AWS Fault Injection Simulator, a fully managed service to define and conduct experiments on workloads to reveal deviations from steady state based on chaos engineering principles. The tool allows you to minimize the blast radius of experimentation through targeted actions, and there is nothing to maintain or deploy or any additional servers to implement to support chaos engineering. While I have covered a lot in this session, and you can learn more about chaos engineering, AWS well-architected, and AWS Fault Injection Simulator by visiting these references. Thank you for your interest in chaos engineering and experiments using Amazon Fault Injection Simulator. To gain more confidence and hands-on experience with AWS, access the digital training built by AWS experts, attend our instructor-led classes by qualified AWS instructors, and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS. Validate your technical expertise with AWS and use practice exams to help you prepare for AWS certification. Thank you again for attending, and we really appreciate your feedback so that we can better understand the topics and services you would like to know more about. So please do take the time to fill out our survey and let us know what you think.